The core engineering challenge in indoor robotic navigation is achieving reliable, submetric positioning in environments flooded with metal shelving and concrete corners. These materials cause severe multipath interference, bouncing radio waves unpredictably and destroying signal integrity. Ultra-wideband solves this with extreme temporal resolution, separating the true signal from its echoes. But that precision requires active nodes with strictly synchronized clocks, driving hardware costs too high for massive warehouse-scale deployment. Bluetooth 5.1 angle of arrival offers a cheaper alternative by tracking spatial phase differences. However, the hardware struggles to keep up with the required math. The physical switching speeds of the analog-to-digital converters limit data capture. Consequently, these systems are forced to discard up to 50% of their in-phase and quadrature samples, crippling real-time tracking efficiency. This comparison matrix maps out a passive angle of polarization system at 2.4 GHz. We bypass UWB's time sync and Bluetooth's IQ complexity. The result? 15 to 30 centimeter precision and multipath immunity, achieved for just $106. Deploying this requires a specific physical infrastructure, a large format 1.25 by 1.25 meter passive reflect array metasurface mounted on the ceiling. Instead of sampling high-speed phase differences or clocking microsecond signal flights, this setup determines spatial coordinates purely by measuring the geometric rotation of the electromagnetic polarization vector. As the robot moves underneath the metasurface, the array backscatters the 2.4 GHz signal. The receiver determines its heading by measuring the differential analog power of that backscattered wave. Tracking raw analog power levels eliminates the need for high-speed digital phase mixing or synchronized oscillators. Achieving ultra-low-cost, submetric precision requires us to stop trying to solve the problem with complex active silicon and rely instead on passive geometric physics. On the mobile receiver side, we use a bionic compass, an array consisting of 6 cheap, orthogonally arranged patch antennas. This diagram illustrates the first critical hardware constraint. We must multiplex these 6 analog signals into a single detector without spatial interference corrupting the data. Standard low-cost reflective RF switches fail here because they bounce signals back into the array. An absorptive solid-state switch, specifically a gallium arsenide SP8T, is mandatory. It uses internal resistors to properly terminate the inactive channels, preventing destructive mutual coupling. To further mitigate dielectric noise between these channels, the PCB routing relies on strict grounded coplanar waveguide traces, built with a 1.2 mm width and a 0.25 mm gap. Removing the solder mask completely over these RF traces is also required to prevent unwanted insertion losses at 2.4 GHz. Moving down the RF chain, the multiplexed signal reaches the detection stage, handled by an AD8317 logarithmic detector. This component has exactly one function. It converts the raw RF power from the active antenna channel into a continuous, usable DC voltage. It operates with an output range of 0.53 volts to 1.2 volts, utilizing a thermally compensated slope of -22 millivolts per decibel. The interface connecting this detector to the microcontroller is entirely minimalist. There are no resistive voltage dividers, just a simple 159 Hz RC filter to strip away Wi-Fi co-channel noise before the signal hits the processor. The analog hardware is strictly responsible for sequentially delivering pristine, isolated voltage levels. All localization complexity is deliberately offloaded to the software domain. That continuous DC voltage is fed directly into an ESP32 microcontroller. This pipeline maps the signal's path, starting with a hardware hurdle. The ESP32's internal analog-to-digital converter is nonlinear at its extremes. The firmware begins by clipping the incoming data stream to operate strictly within the linear 0.15 to 2.45 volt region. Because the digital signal processor requires linear power rather than logarithmic decibels to calculate angles, the firmware then applies an exponential inverse function to linearize the readings. With linear power established, the system extracts the Stokes parameters, represented as S1, S2, and S3. This is done by calculating the difference in linear power between opposing orthogonally paired antennas. This specific differential subtraction perfectly cancels out common mode background radiation and local thermal noise. Next, the firmware applies a Clark transform, projecting this redundant three-phase Stokes system down into a continuous two-dimensional Cartesian plane, defined by Q and U components. The final geometric calculation applies a four-quadrant arctangent function to Q and U. This resolves the exact angle of polarization, without any angular discontinuities. But this two-dimensional math assumes a perfectly level robot. In the real world, we have to account for platform attitude. If the mobile receiver experiences pitch or roll as it navigates an uneven floor, its local polarization map rotates out of alignment with the ceiling metasurface above it. To correct this, the system integrates an ICM 20948 inertial measurement unit. The IMU feeds real-time attitude data into the pipeline, dynamically projecting the tilted local Stokes coordinates back into the global spatial reference frame. The final environmental threat is non-line-of-sight multipath reflections. When the radio frequency signal bounces off metal infrastructure, it becomes scrambled and depolarized. The system tracks this degradation by calculating the degree of polarization, a metric that quantifies the geometric purity of the incoming signal. This metric triggers the system's ultimate defense, a dynamically weighted Kalman filter, governed by this covariance equation. It operates on a strict inverse square relationship. If the degree of polarization drops due to a severe multipath bounce, the algorithm exponentially suppresses that specific reading. It effectively ignores the ghost signal in real time. The ESP32's firmware is designed to mathematically repair the mechanical and environmental vulnerabilities that would normally destroy the accuracy of a cheap analog receiver. Through this pipeline, the architecture achieves sub-centimeter positioning precision, utilizing just 95 hours of firmware engineering and $106 in off-the-shelf parts. This photograph shows the physical reality of a bionic polarization sensor, anchoring the theoretical array geometry in a tangible 3D printed form factor. If the technology is this efficient, the obvious question is why we can't shrink this hardware down to tiny passive RF tags, similar to standard RFID. The limitation is fundamental to the 2.4 GHz frequency. At this band, the 12.5 centimeter wavelength establishes severe electromagnetic boundaries that prevent aggressive miniaturization. Squeezing resonant RF elements too close together causes destructive mutual coupling. This crosstalk warps the backscattered wave and completely corrupts the spatial identifier. To prevent this interference, the architecture strictly requires the continuous, large-format 1.25-meter reflect array on the ceiling to operate cleanly. There is also a final environmental vulnerability intrinsically tied to the system's ultra-low-cost design: material degradation. Prototyping the ceiling metasurface with corrugated cardboard provides a cheap dielectric substrate, but it is highly risky in industrial environments subjected to extreme relative humidity. As the cardboard absorbs moisture, its dielectric constant changes. This causes severe input impedance shifts and increased insertion losses, requiring rigorous degradation modeling before this setup can be mass deployed. Elite engineering is never about building perfect hardware in a vacuum. It is the art of finding the exact mathematical compromise that makes physical reality economically viable.